Hello again, everyone. This is part 2 of our notes on 6.3 polar coordinates. What we did in the first part of these notes, we talked about what is a polar coordinate and how we can plot them with some additional practice therein. What we're going to do in this video is kind of explore how we can move back and forth between rectangular and polar coordinates. As you can see here, we're going to convert these coordinates to rectangular and rectangular back to polar. So what we saw in our last few units, specifically when dealing with values on the unit circle, is that any angle we had, we effectively turned into a right triangle. And if we think back to our coordinates and how we used them, we used cosine as our x value, the coordinates on our unit circle, and sine for our y value. So and while we won't just use r as our radius or our hypotenuse every time here, in this case, we can just call it r, right? So we're no longer on the unit circle, but a lot of the fundamentals that we've seen there are still being used. What this allows us, it allows us some moves that we can make between forms. We know that the sine of theta, in this case, would be y over r. And we could solve for y. We could find that y equals r sine theta. Similarly, we could do the same thing with cosine. We know that the cosine of that angle theta will be x over r. And with some manipulation, x will equal r cosine theta. These two formulas are really nice ways to move between the forms. Right? If I have a r and a theta value, I can find them with my, I can use those to find my y value, and similarly, I can use those same values to find x. There are two other formulas that relate x, y, r, and theta. The first one is our third kind of standard. Yeah, we can use tangent of theta, and in this case, that would represent y over x. And the third one is really just our Pythagorean theorem, right? X squared plus y squared equals our hypotenuse, r squared. So these are the relationships, these formulas that we will use in order to convert between rectangular and polar coordinates. So with those in mind, let's take a look at some examples. So example 4 here, we can see that we have a polar coordinate of 2 pi over 2. Well, we can approach this a few different ways. I think the easiest way is just to think about where this coordinate is. In the direction of pi over 2, which on our coordinate would be in this direction of that blue x, I travel 2 units. I'll just clearly here we can see that our coordinates should be 0, 2. Now, if we didn't notice that right off the bat, I could find my x coordinate with r cosine theta, which in this case would be 2 times the cosine of pi over 2. We've done enough evaluation here to know that the cosine of pi over 2 is 0. And then we could find our y value, r sine theta, which is going to be 2 times the sine of pi over 2. We know that the sine of pi over 2 is 1, and that 1 times 2 is 2. So our coordinates, however we go, will get us 0, 2. If we are working in the direction of, say, pi over 2, or pi, 3 pi over 2, 2 pi, any of our quadrantal angles, right, north, south, east, west, if we were looking at a compass, the distance we travel, we're just traveling along our x and y axis. So don't overcomplicate things. I definitely recommend using a small little sketch like this to help make sense of things. Now, it's also possible that we get something like example 5, where we have 1 at an angle of negative 110 degrees. So this one is a little bit trickier. Negative 110 degrees is not on our unit circle. That would we don't really have a way to evaluate this without a calculator. So for our x value here, we're going to take 1 times the cosine of negative 110, and y will be 1 times the sine of negative 110 degrees. Make sure you're in the correct mode in your calculator. Make sure you're in degree mode, but just plug this in as we see it. And what we will find is that our rectangular coordinates are negative 0.34, negative 0.94. Again, those values are coming directly from our calculator. They are just kind of plugging in as we see them. To use our calculator, we can do this very same process. Where we're going to use is the angle menu. The way you can get there is by hitting, I'll just try to put our buttons, second, and then the apps button. And what you'll see as you scroll down the list are two different conversions. And I'm just going to write them out here. So our input, when we plug this into our calculator, is an R value and a theta value. This option here that you see on the screen will get us our X coordinate. And then if I use something very similar, I will get the same output from my calculator. Oh, sorry, I made a mistake there. This should be RY. What these two options get us, it's converting us from polar, oh, sorry, wanted a highlighter there. Wanted a polar converted to rectangular and get the X value. And then the second option is converting polar to rectangular and getting the Y. So we do have to go through the process on both of them and plug both of them in, but our calculator can do this work for us. Let's look at some more examples. I have one from our page here, and then I'm actually going to add one that isn't in our notes, but I'll add that in just a moment. So here we have, we're trying to convert an entire equation into a rectangular equation, a polar equation into a rectangular. So what we have here is r equals 3 cosine theta. Now we have all those values. We know that r squared equals x squared plus y squared. We know that x equals r cosine theta. We know that y is r sine theta, and we know that y over x is tangent theta. So our goal here is to rewrite this equation in terms of x and y instead of r and theta. So I'm really looking for an y equals something, x equals, if we have a circle, it may be x squared plus y squared. But our goal is to get rid of our r and theta values and try to create x and y. So what you may notice on this particular equation, we don't really have cosecant in our bag of tricks. So we can say r equals 3 divided by sine theta. And even if we're not sure where to go next, maybe our instinct is to clear that fraction, multiplying both sides by sine theta. I will have r sine theta equals 3. Well, that's actually very helpful for us. We know what r sine theta is. R sine theta is the same as y. So our simplified equation here in rectangular form is y equals 3. We've gotten rid of our r's and thetas, and now we just have just a y in this case. I want to create one more. I'm just going to add to our notes. It's going to be r equals negative 6 cosine theta. Now here we have to use a little bit of a different technique. As we look at this, we have an r on one side, we have 6 cosine on the other, but we don't have enough to convert either. So what we want to do here is multiply both sides of our equation by r. By doing this, we'll create r squared on the left side of my equation and negative 6r cosine theta on the right. Why does that help us? Well, r squared is the same as x squared plus y squared. And negative 6r cosine theta is the same as negative 6. If you don't recognize this is actually a circle, which I'm going to complete the square and rewrite in standard form. And we could simplify this to x plus 3 quantity squared plus y squared equals 9. So r equals negative 6 cosine theta. we can convert that to the equation of a circle that we saw earlier in the year. All right, we have a couple more problems we're going to work through here. I think we have 4 remaining. We're going to keep fighting through. When we convert to polar coordinates, it takes a little bit more work. We really need to plot the point first. So that's going to be our first step. I'm going to add this to the right-hand side. We're going to plot our point and create a triangle. So this point, -2, +2, is up here in the second quadrant. And that point, like any point on our rectangular grid, can make a right triangle. So what we're looking for, our theta value is really this angle out here. And our r value is really the length of this hypotenuse. We know that this is -2 and this is 2. So I'm going to find r using the Pythagorean theorem. So I'm going to say that 2 squared plus 2 squared equals r squared. 8 equals r squared. So r equals 2√2. And then my final step here, I'm going to use trig. I'm going to say right triangle trig to find the angle. So this is an angle that has a tangent. So the tangent of theta equals -1, and it is in the second quadrant. This is a unit circle value. We know that in the second quadrant, tangent has a value of -1 at an angle of 3π/4. So our final answer here, our our polar coordinates, will be an r value of 2√2 and a theta of 3π/4. There are a few more examples here. As usual, I'd like you to pause the video here and try 7 and 8 on your own. And we'll kind of come back and debrief in a moment. All right, let's see how we did. So again, we have to construct this triangle for number 7. So what I did, I constructed that 1 unit to the left, √3 is our height. And using our Pythagorean theorem, we end up with 3 plus 1, take the square root of that 4, and we get our radius, or not a radius, just an r value of 2. I used the tangent function here, and I found that the tangent of theta, which exists right here, is -√3. This angle occurs in the second quadrant, and it is actually a unit circle value. That -3 comes from a theta value of 2π/3. So there we have all we need for our rectangular coordinates. Excuse me, I keep making that same mistake. We've moved from rectangular to polar. On number 8, we will need our calculator for this one. We have our classic 3, 4, 5 Pythagorean triple here. So the r value is nice and easy to find. It is 5. Once we have all 3 sides of our triangle, we could use sine, cosine, or tangent. But whatever we do, we will have to plug into our calculator. If we are in radian mode, as we often are for polar coordinates, we would get 5, 0.93. That 0.93 is representing radians. If we wanted to use degrees, we get to the same answer of 5 and 53.13 degrees. So we did this kind of the long way. We can also convert with our calculator as we did on the previous page. Again, we're in that same angle menu, second apps to get there. And then using these 2 options on our calculator, they are options 5 and 6. This will take an x and a y value as an input and output either an r or a theta, depending on which of the options you've chosen. Let me just write that in there. This is option 5 on the angle menu, and here is option 6. We have one more problem to finish up here. On the last page of our notes, we have a rectangular equation. It's an equation of a circle, and we're going to convert it into a polar equation. Now, as I look at this, directly substituting is going to be a little tricky. So before I do that, I'm going to simplify and expand this as best I can. I'm going to expand what I have on the left. Sorry, I missed the 2 there. And now I'm going to simplify. I'm going to rewrite this as x squared plus y squared minus 2x equals 0. What this allows me to do now is to use some of my direct replacements, our direct substitutions. I know that x squared plus y squared is the same as r squared. And I know that x is the same as r cosine theta. Now we can continue solving this as if it were an equation, factoring out an r value. We would have r minus 2 cosine theta. And if I were to solve each of these, I would get r equals 0 and r equals 2 cosine theta. This one on the right is our preferred answer. What this answer on the left represents, it represents the polar equation, right? That center dot at the middle of our graph. And it's basically trivial. It doesn't really mean much for our purposes. So the equation that we're looking for is this r equals 2 cosine theta. We know that we're done because we have an r equals statement with only theta as our other variable. Nice work, everyone.